Hello, welcome back once again. Today we have this interesting number theory problem. We're asked to find the last two digits of 9 raised to the power of 8, raised to the power of 7, raised to the power of 6. This power continues up to 2, then raised to the power of 1. Interesting, right? And we know that this number is crazily large, right? So how exactly are we going to solve this problem? Now, let us remember that whenever we are asked to find the last digit of a number, then we need to divide the number by 10 to find the remainder. So finding the last digit of a number is same as finding the remainder when the number is divided by 10. If you extend it to last two digits, then we need to divide by 100 and find the remainder, right? So this implies that this question is same as evaluating 9 to the power of 8 to the power of 7. This continues to the power of 2 to the power of 1, then in mod 100, right? Very interesting. Okay. Now let us recall from Leonhard Euler that whenever we have A raised to the power of B and we're evaluating this in mod n, if the GCD of A and n is equal to 1, then this implies that A to the power of B must be congruent to A raised to the power of B evaluating in mod of the Euler phi of n and then the base in mod n. Okay? So here, think about this, 9 and 100. Their GCD is 1, right? So which shows that they are indeed co-prime. Then we need to evaluate the Euler phi of 100. So what is the Euler phi of 100? So it is going to give us 40. I've done video on how to calculate the Euler phi of numbers, okay? So now, according to this theorem, we need to evaluate this power starting from 8 up to 1 in mod 40. You can see here A to the power of B is equal to A, then raised to the power of B in mod Euler phi of n, and then mod n, okay? So this implies from here that we're going to evaluate 8 to the power of 7 to the power of 6. This continues to the power of 2 to the power of 1 in mod 40, which is going to be very interesting. But we have a problem here. Can you see that 8 and 40 are not co-prime? The reason, because the GCD of 8 and 40 is not equal to 1, right? So what do we do from here? Then we split the modular, or the modulus, I mean. So here, we're going to split 40 as 8 multiplied by 5. So we split this modulus. So splitting this, then we say that we have first A sub 1 is congruent to, we're going to evaluate 8 raised to the power of 7 up to raised to the power of 2 raised to the power of 1 in mod, the first one here, 8. Which is very obvious that this is going to give us just 0 mod 8. Why? Because 8 divided by 8 has a remainder 0. Then we have A sub 2, which is congruent to this 8 to the power of 7 to the power of 2, then to the power of 1. Then evaluating this in mod 5, this second one here. And we know 8, the base here, divided by 5 has a remainder 3. So this is congruent to 3 raised to the power of 7. This power continues up to 2 raised to the power of 1. And then mod 5. Again, we can say that the GCD of 3 and 5 is equal to 1. Then we evaluate the Euler phi of 5. 5 is prime. It will give us 5 minus 1, giving us 4. Then from here, we need to evaluate this power in mod 4. Okay? So we have here 7 raised to the power of 6. This power continues raised to the power of 2 raised to the power of 1. Evaluating this in mod 4. 7 divided by 4 has a remainder 3. So we have 3 raised to the power of 6. This continues raised to the power of 2 raised to the power of 1 in mod 4. Okay, again, 4 and 3, they are co-prime, right? So we need to evaluate the Euler phi of 4, which is given us 2. So according to the theorem from Euler, so this is congruent to 3. Then this power here, 6 raised to the power of 5, raised to the power of up to 2 up to 1. Then in mod the Euler phi of 4, which is 2, right? And then we have here mod 4. So we know clearly 6 divided by 2 has a remainder 0. So we have 3 to the power of 0. Then in mod 4, which is given us, this is congruent to 1 mod 4. Okay, so recall back. Remember, we are evaluating 7 to the power of 6 to the power of 5 up the way to the power of 2 to the power of 1 in mod 4, which is congruent to 1 mod 4, right? Therefore, we say that, sorry for that, a sub 2 is congruent to 3 raised to the power of 1, and then mod 5, and this is congruent to 3 mod 5. So we can see a sub 1 is congruent to 0 mod 8, while a sub 2 is congruent to 3 mod 5. So we need the smallest number that when it is divided by 8 has a remainder 0, but when it is divided by 5 has a remainder 3. And we can easily say that this smallest number must be 8, right? But let us prove it using the Euclid's method. Sorry for that. So we have this smallest number. If it is x, then we have x is congruent to, sorry for that, 0 mod 8. Then we have x is congruent to 3 mod 5. So from here, we know the general solution here, x equals 8k plus 0, which is 8k. Then this is Euclid's method we're using. We are not using the Chinese remainder theory. So here, x is congruent to 3 mod 5. 8 is here, so it becomes 8k. Replacing for x in the second equation is congruent to 3 mod 5. This is also congruent to 8 mod 5. So divide both sides by 8. It implies from here that k is congruent to 1 mod 5. This also implies for general solution for k equals 5m plus 1. So we substitute here for k. We get x equals 8 times k will be 8 times 5m plus 1, giving us 40m plus 8. We can see it here. This is the remainder we're looking for, and that is the x value as we stated earlier. Okay, so therefore we now have that 9 raised to the power of 8 raised to the power of 7 all the way raised to the power of 2 raised to the power of 1. Evaluating this in mod 100 is similar or congruent to 9 raised to the power of 8. Yes, then in mod 100. So this is congruent to, using exponentiation, we get 9 to the power of 4 squared. Mod 100, this is where algebra comes in, right? And then here, 9 to the power of 4, remember this is 6561. Remember we have mod 100, so we pick out the last two digits, giving us 61, then squared, and then mod 100. So 61 squared is giving us 37. So this is giving us 3721 mod 100. So which is congruent to 21 mod 100. So this is our solution. And what's the solution? That 21 is the last two digits. Very interesting. Did you enjoy the video? Please, if I receive like about 1,000 likes on this video and more views on this video, I'm going to make more interesting videos on number theory. Okay, thank you for watching. If you enjoyed the video, kindly like, subscribe, and also don't forget to share this video.